so as to give all the speakers an opportunity for 25 minutes of talk. Thank you for coming after lunch. This is very good of you. I hope you stay awake. I'm sure you will. We have 3 very interesting talks ahead of us. Our first speaker, we are really going to span the globe. We're going from Italy to the US to Australia, and gives you 3 interesting perspectives. Our first speaker is Stefano Nativi. He's the coordinator of the Earth and Space Science Informatics Laboratory in the Italian National Research Council. Stefano.
Thank you. Thank you very much. Okay, let me start. Okay. Okay, thank you. So this is a very brief outline of what I'm going to show you. First of all, some background, so why we decided to be active in this particular research area, some international programs which are really interested in this area, and so which are the main connection with these different programs. And then I will focus on the infrastructure for interoperability for this particular area, and therefore the global monitoring for environment and the civil protection domain, in particular our experiences with the Cyclops project funded by the European Union. And then I will finish with a few slides on what is called a vision that is towards European infrastructure for civil protection boards, agencies, actually. So why we decided to work in this area? Because as it was explained today in some presentations, in some beautiful presentations, we need to support environmental policymaking and risk managers. And from our point of view, that means mainly to integrate the multidisciplinary knowledge in order to, to better capture the so-called Earth system science, the so-called Earth system in a very, global and entire way. This is useful for many societal benefit areas, and we are particularly devoted to serve the civil protection area, environmental monitoring, sustainable development. So we address this important problem to shift from a so-called traditional data-centric approach to a more advanced service-based solution, the so-called service-based approach for this area, so for Earth system science. This is important, and it is important therefore to leverage the so-called cyber infrastructure benefits and support these distributed multidisciplinary collaborative teams. Of course, this is a big challenge, not only for scientists, but also for information and communication people. Okay, this approach, of course, is addressed by many programs, several of them funded also by the European Union. And here we have some examples. In particular, we have many decision support systems for the different civil protection agencies. We have the so-called Earth and Environment system of systems, such as the GEOS. GEO is the system of GEO, the Group for Earth Observation. Then we have the EU, the European Union, GMES, Global Monitoring for Environment and Security, the new CIS or SACE EU program. We have many special data infrastructure, such as the European Directive INSPIRE, the US National SDI, the Chinese NFGIS, the many observatory systems, in particular those dealing with the biodiversity and ecological systems, such as the NEON, the BON, the GEOS-related biodiversity program, which is called GeoBON, the European BON. and the Science Digital Library. Of course, this is a very technologically driven approach. And all of these have in common the same approach, which is called the information modeling-based approach. That means to consider as key factors interoperability and metadata sharing. These are important in order to discover, access, and share not only data, but also services, knowledge, best practices, and so on. And they generally implement interoperability and they share metadata, adopting a SOA approach, service-based approach, and applying international standards and or best practices. So this system way to do things, to federate different legacy systems, is mainly based on loosely coupled systems which are locally autonomous because they implement interoperability at different levels, mainly through international standards. So standardization is a very important point here, and when we say standards, we have to conceive and achieve these at a very international way and at the lowest common component way. So this is important. These are the many organizations working, which have been working at the different levels in order to develop these international standards for interoperability. Okay, so this is the general background, and we decided so to follow this approach, which also implies to develop infrastructures, different infrastructures for the different domain resources. So domain resources are seen and are used as quite different infrastructures. And therefore, resources, as I mentioned, not only data set or data, but also sensors, knowledge, best practices, and networks also. So here we can distinguish among three main interoperability levels and therefore infrastructures: the grid, or sometimes also not only grid, but also web, computing level, the geospatial interoperability level, which is particularly important if we want to establish the so-called digital Earth approach, and the GMES, the global monitoring for environment resources, that is services useful for the Earth system science. On the top of this last level, we may serve the different scientists in a very general and unique way. So we have a different area, the different disciplines here, and in particular, then we have a very interesting and specific area, which is the risk management. And of course, we are interested in that particular area. So it's useful to have at least three main different domain interoperability levels dealing with different services data set. Generally speaking, we have different resources. And of course, we have to establish interoperability resorting to standardization. These are some of the main standards useful in order to implement interoperability. Okay, so I would like to spend some words on the first two layers, the GMES or Earth System Science Platform or infrastructure. As I said, this is particularly important because it is pursued by a EU-funded project, EU and ESA, actually, European Space Agency funded project, which is called GMES, which is a concept useful in order to create value-added services for decision makers. And in particular, the final report of the GMES initial period recognized the civil protection domain as one of the most interested one and outlined the importance to develop infrastructure and virtual organization services for that particular area. And actually, we can recognize at least three main stages when these people work: the pre-disaster, the response, and the post-disaster phases, and each of these must be characterized by specific services and therefore specific resources. And we should be able to develop them in a quite comprehensive and standard way. And as I said, this is the top level, the top domain infrastructure, which must be based on a set of general geospatial services. In fact, environmental policymaking services must be underpinned by these general geospatial resources in order to shift from a centric approach to a more advanced service-based solution. And this is the kind of services that we consider devoted to that particular level, in particular data models and services dealing with concepts such as general features, imagery, gridded and coverage resources, observation and measurements, geospatial coordinate reference system, geospatial sensors, quality, metadata, and so on. So these are quite general concepts, and of course the so-called related services are quite general and must be must be useful in order to support then the specific domain of the civil protection area. And here we have three different, or at least three main different levels where we must work on. The first one is when you acquire data sets or you model something, so you must do it in a quite general and standard way. Then when you extract the knowledge and you shape in a very harmonized way your data set and knowledge. And the third stage is when you publish and you encode your data set and products. Okay, so we actually decided to start from this general approach, from these concepts, from this stack view, and to develop a specific platform for the civil protection agencies. We have done this in the framework of this EU-funded project, which is called Cyclops, and we had some civil protection agencies on board, in particular the National Protection Agency from Portugal, from Italy, France, and the local protection agency, one local protection agency from Greece. Then, of course, several ICT, information and communication technology partners. And the main objective of this project was to bridge the existing gap between the grid community and the so-called civil protection and GMES people. And we had used the previously described approach in order to fill this gap. These are the main needs coming from civil protection people, so to access infrastructure, run models, and search data in a real, or I would say near real-time way, to control sensor networks and the acquisition systems, to share geospatial data set and knowledge in a quite standard way, to formalize the knowledge, and to adopt the strict data policy and the security requirements that civil protection generally use. So these are the main challenges, and we try to apply the system approach in order to conceive and test a particular platform for addressing these needs. And this was called, of course, the Cyclops platform. This is the platform. It's based on a grid middleware, actually the European grid middleware, the so-called EGE middleware, the G-Lite platform here, which virtualizes processing data and instrument services And on the top of these, we conceived a set of special data infrastructure services. And in particular, we can recognize two main kinds of services: advanced grid services in order to manage the knowledge, the concepts, and the other kind of services is called the geospatial resource services in order to discover and access and process these kind of concepts. And this is the Cyclops infrastructure. In a certain sense, this may be considered as a sort of cloud, a very particular cloud structure, cloud system. And now it's possible to develop business logic and a presentation specific for that area, along with the security infrastructure and the interoperability platform, which means to implement international standards. We have a Cyclops platform. And now you can implement your near real-time services and tools. And we can recognize the three different platforms, three different infrastructures here. Now I want to say something more about these geospatial resource services because this is a EU-funded project. It is based on the EU, on the European grid platform, and so we have considered the geospatial resource services coming from the European directive, INSPIRE. And here you can see some of the services recognized by this European directive, such as registry, discovery, view, download, transformation services. So we have to implement, and then we tested some of these at that particular level. More generally, at that level, at the SDI services level, we have a lot of other quite specific services. In particular, these are recognized by ISO, and they have some taxonomies here. For example, the human interaction services, viewers and editors, model information management services, such as access of that particular data set, features, coverages, maps, and so on, workflow, of course, services, processing service, but here specific processing services, such as spatial, thematic, temporal, and metadata processing services, then communication and system management services. So we have to work at that particular and specific domain level. And if I get down to work, with the so-called processing service for special aspects, here I have other very specific semantics, such as coordinate conversion, coordinate transformation services, auto rectification, special subsetting, feature matching, and so on. So again, we have to place here particular kinds of services. So Cyclops adopted a quite normal structure for its development. So we started from the business process study, then we developed use cases, system requirements, and then we consider all these studies in order to design that particular Cyclops platform. Then we decided to test the platform for two valuable use cases, and we achieved a couple of proof of concepts, and all that experience was then summarized in a couple of documents. The first one is called Towards Agreed Guidelines for Innovation Strategies for Civil Protection Systems, and the second one is called Research Strategies for the Development of a Civil Protection infrastructure. So just a few slides on the two proof of concepts. The first one is called G-Risico. G stands for grid, and Risico is a model actually used by the Italian Civil Protection Agency for a forest fire risk assessment, and it is linked, I mean, this theme is linked with the preview GMES service, and we try to port this existing model with actually operational model in our platform. So using the approach that I described before. And so we can recognize the three different levels: the GMES CP level, the special resource level, and the grid computing level. And this is taken from the GUI of the G-Risico prototype, so you can select a particular area. Of course, also cross-border areas are valid. You can discover and get a data set coming from France or from Italy or from any other, nation, as far as Meteo and the land data sets are concerned. Then you can select the number of jobs or the temporal response, and so you can run your model. You can have several runs. You got 4 outputs for the risk assessment, and because you have this grid platform underpinning the entire system, you can zoom in and you always have quite resolute outputs. The same was done by the French partner for the flood forecast, and this is linked to the GMES flash flood anticipation service. Here, the actual operational model ported into our system is called SPCGD. Just keep these, which are based on the developed proof of concept. Both run on the implemented EG system. These are the nodes. And so we demonstrated actually that if you use a grid computing platform, you get scalability. That means to improve several features such as output data, resolution, model complexity, time response, widen, and to widen the cover area. If you use the geospatial standard infrastructure, you have flexibility and interoperability. And here are some of the main benefits. Well, these are the two achieved deliverables. The first one is conceived for research activity and funding decision makers. And we identified main research themes and topics. This is a very oversimplified table. So research themes are grid infrastructure enhancement, advanced middleware for civil protection applications, security, civil protection, application enablement, and interoperability. The other is called innovation guidelines, conceived for the civil protection innovation decision makers. Here we identify the main obstacles and we propose possible solutions. Oversimplified table here, we have some themes, main obstacles, and proposed strategies. My very last slide is on how we can, pursue these European infrastructure for civil protection agencies. And so we learned from Cyclops, and we actually decided to start some actions in a 2 different ways: top-down actions and bottom-up actions, of course, considering our platform, top-down and bottom-up. And so we promoted some sessions and a forum on the civil protection domain at the Open Grid Forum. We promoted an EGI civil protection group in the framework of Earth Science Cluster. We promoted the liaison between the European Geosciences Union and OGF and OGC, Open Geospatial Consortium. As far as bottom-up actions, we promoted a grid geospatial research component for the EGI Earth Science Cluster, and we started the so-called GLITE OGC Web Services Working Group in order to support this interoperability effort between the grid and the geospatial standard resources. And okay, I think that's all. If you need more detail on Cyclops and on the GLITE OGC Web Services, these are, I guess, 2 valuable links.
Thank you very much, Stefano.
Okay, you're welcome.
Our next speaker is Heidi Alvarez. So we're leaving Europe and going to the US, but she will take us even farther afield. She's the principal investigator for global cyber bridges at the Florida International University. Heidi.
Buenas tardes. ¿Qué tal? You might notice I don't have, oh, I'm getting mic'd up. I don't have a Spanish accent. I grew up in New York. Thank you. No. Okay. So let's see if we can get this thing started. There we go. Okay, so it's my pleasure to be here. Thank you, Jacqueline, for the invite. I'm going to speak with you about International Hurricane Research Center at FIU, my university, and cyber infrastructure-enabled hurricane mitigation. You can see the cyber bridges label there. That's the project under which we do the work. Okay, so here's my outline. The first few slides are courtesy of Dr. Steve Letterman, who's the director of the International Hurricane Research Center on our campus in Miami. And the next set of slides are from Global Cyber Bridges, one project of several under that umbrella. And this is a student-driven project, so we'll talk to you about background and motivation, the role of cyber infrastructure and global cyber bridges, the hurricane mitigation project overview, the status, and cyber infrastructure contributions to the work, and then we'll have our conclusion, all in 25 minutes or less. So here are some pictures. What happens in a hurricane? Wind damage, storm surge inundation, freshwater flooding, beach erosion, and the International Hurricane Research Center Laboratories is involved in trying to mitigate some of this damage. There's insurance, financial, and economic research. The IHRC is dedicated to defining the hurricane threat to the economy, develop the first public catastrophe model to predict damage and insured losses. The center provides technical assistance to hurricane vulnerable stakeholders, quantitatively assesses vulnerability of coastal areas to storm-induced beach erosion and hurricane surges, and utilizes advanced airborne laser mapping and computer animation for coastal research. There's also the social science aspect of the research to study how individuals and groups respond to hurricanes, formulating methods to improve the resilience of the community, and then there's wind engineering research, investigating solutions to making homes and buildings more hurricane resistant, measuring hurricane surface winds, and conducting wind pressure and impact testing. So you can see they do some of this work using a special kind of radar mapping that's very helpful, and they have a plane flying around. So a case in point is Hurricane Katrina. There's a satellite view of it hitting New Orleans. The Wind Towers team and portable Doppler radar unit coordinated the data collection from Katrina. And I won't have time to get in depth on weather research, forecasting, and modeling, but there's so many different models, and really expert meteorologists learn to read them and come up with a prediction. And so the more data they can collect, the more accurate the modeling can be. So the storm surge prediction was done by the International Hurricane Research Center. And you can see what happens when it hits. That's somebody's house. I guess the disconnect is being able to predict it and actually getting the population to respond in time. It's a challenge. So this machine is called the Wall of Wind, and it's fabricated by manufacturer Diamondback airboats. So any of you ever been to Everglades? No? Yeah, one person. So we have these big boats that are powered, like, it looks like a fan, you know, but it's huge and noisy, and so they use that to make this. It was delivered in January 2005, and presently developing the active control system that will be duplicated in phase 2. This project is very well financed and funded. So that's the first part about the International Hurricane Research Center. Now we're getting into part 2. So what is Global Cyber Bridges? It's a grant under a program called Cyber Infrastructure Training, Education, Advancement, and Mentoring in our 21st Century Workforce, CI team. 3-year award. We began in October 2006. We'll run through the end of this year. It was funded at $765,000 by the National Science Foundation. And the 3-year award followed a 1-year pilot project to proof of concept to help train FIU scientists and engineers to advance their research through cyber infrastructure. So today I'm only talking to you about one of a number of projects under Global Cyber Bridges. We work with scientists and engineers in all different domains. This is the one that's particularly apropos to our session. So as you'll see on the advisor side, we have, in addition to me, and it's really my privilege to be in the lead position and work with these people, from computer science at FIU, Dr. Sajadi, Dr. Willoughby, who's an earth scientist at our university and a distinguished research professor, Dr. Kainan, who's with the Computer Network Information Center of the Chinese Academy of Sciences, and Dr. Esteban Klua, who's with UFF, which is a lovely university in Rio de Janeiro. And our project is international between US, China, and Brazil. Okay? So on the student side, it's led by one of our PhD students at FIU, Javier Delgado. And we have Wendy Wan, who's with CNIC of CAS. And then we have 2 students at UniSantos and UFF in Brazil. And they're all leading different aspects. So altogether, and you'll see this definition later, but WRF means Weather Research and Forecasting. So this only lists the students that are fellows of Global Cyber Bridges. It's actually got even more students working on hurricane mitigation. And as you'll see, there's a portion of it that's the visualization portion. So let's look at some background. Hurricane mitigation is computationally intensive, just as Stefano's presentation pointed out to us that all of these disaster mitigation recovery programs need a lot of computational power. Improvement requires cross-disciplinary expertise. We need high-performance computing, meta-scheduling, resource allocation, workflow management, in our case, weather modeling, weather research, and forecasting. So the research motivation, it's sort of self-evident, but it's hard not to show you a bunch of pictures when you do this sort of presentation. Hurricanes cause coastal regions financial and personal damage. The damage can be mitigated, but impact area prediction is inaccurate. Simulation using commodity computers is not precise, and we have some alarming statistics. 40% of small to medium-sized companies shut down within 36 months if forced to close for 3 or more days after a hurricane. Local communities lose jobs and hundreds of millions of dollars to their economy. And this last bullet is a real financial driver. If 5% of businesses in South Florida recover 1 week earlier, then we can prevent $219 million in non-property economic losses. So why apply cyber infrastructure to research and learning? This is not just about hurricane mitigation, it's a bigger picture. Our philosophy is that we're preparing for a globalized workforce. Innovation is now driven by global collaboration. Diverse and complementary expertise needed to solve research problems. We can enable transparent cyber infrastructure, and in global cyber bridges, our students are the bridge. They bridge between disciplines using technology, and they will take this forward into their careers. So you have 2 of our student leaders pictured there. And we had them present live last year at the Chinese American Networking Symposium. So the Hurricane Mitigation Project overview. The goals of the project are high-resolution forecasts with guaranteed simulation execution times, human-friendly portal, high-resolution visualization modality, and high-resolution hurricane forecasting. We create a distributed software model that can run on heterogeneous computing nodes at multiple sites simultaneously to improve speed of results, resolution of the numerical model, scalability of requests by interested parties. In other words, we need to grid enable the weather research and forecasting software system. So why so many processors? This is a big why. Parameters, I can't even say this word in any language. Well, the parameters that we put into the model on the 10-kilometer grid cannot differentiate different modes of convection. So what we're trying to do is narrow it down and blow it up, to be able to visualize smaller area and see it larger, okay? So this is a very simple model, and it shows being able to run this software, the WRF. On one side, at Scenic, you're in Beijing. Other side, at FIU, you're in Miami. And we've been able to set up these grid clusters in both locations and share the job flow manager and share the meta-scheduler and then run simultaneously to get better results. Additionally, like the last presentation, we want to show an easy-to-use GUI interface, in this case, this web portal. And the little figure there is your meteorologist. So we put a meteorologist in front of this system, and we let them pull in all the parameters they need. So here's a picture of the WRF portal high-res visualization, and looks quite nice. It's on-demand weather forecasting, and it's efficient resource utilization and grid computing. So the result is that we can do modeling for weather research forecasting behavior. There's some pros and cons here. The paradox of computationally intensive jobs. Well, first, if you underestimate execution time, the job dies. And if you overestimate execution time, the queue time is prohibitive. So grid computing drawbacks are that they're less reliable than cluster computing. There's no built-in quality assurance mechanism, and hurricane prediction is time sensitive, so it needs to work around this. Now, some of you can think back to when you were doing your thesis or your dissertation. These problems are good because they give you something to put your teeth into, and that's why we have so many grad students that want to work on a project like this. So the meta schedule addresses the quality assurance issue, and to predict execution time, they model the software. And here's a quick and easy way of looking at the iteration of the process. You take your mathematical model, which is that WRF. You do profiling, parameter estimation, code inspection, modeling, and you just keep going. The current execution prediction accuracy. It's adequate accuracy on multiple platforms. And we run this on different clusters. We have an 8-node cluster, which is a GCB training cluster. We have another 16-node, 64-bit cluster. And we have different simulated CPU speed and number of node executions. And this is pretty cool. We collaborate with the Barcelona Supercomputing Center. And so part of this work is also run on the supercomputers there. Now, shift gear a little bit. I said that in addition to the computation, there's also the visualization challenge. And so for this, we brought in collaboration to use a scalable adaptive graphics environment, or SAGE. And SAGE was developed by University of Illinois Chicago, the Electronic Visualization Lab. It's scalable. You can have hundreds of screens. It's built with high-performance applications in mind. It's extensible, and it provides APIs for creating custom SAGE applications. Porting an application is not trivial, and those are the words of our students. It isn't trivial, but it's worth the effort. And you have a picture here of the SAGE tile display wall in Beijing. We have one at FIU as well. So we've had students working on enhancements to SAGE. On the one side, we wanted remote desktop enhancement. So a responsive remote desktop modality is essential for collaboration and e-learning. And again, you get into the social science of having what is essentially a virtual organization for scientific research. And the users can share their display for all collaborators to see. Non-portable applications can also be displayed. So they've been working on having web browsers run on that wall. On the other side, I think the most fun we have is that some of our students took a Wiimote, which is a Nintendo game. You all have that at home, right? And forget the mouse. It's really hard to drive a mouse on such a wall. So they gave a better human interface. And we're still getting all the kinks out before we go into production, but they have a lot of fun with that. So Global Cyber Bridge's overall contributions to weather forecasting. Students in different scientific fields from 3 different continents are exposed to the problem through a remote class. Grid computing related methodologies for addressing these problems have been presented, and collaborative publications are in progress. And one of the best results we've had from global cyber bridges is we have over 20 peer-reviewed publications, and they're available on cyberbridges.net. So this group is working on their publications, and we encourage all of our students to do that. It helps them when they graduate and to get jobs and so forth. The visualization. Based on the difficulties we had in the class, and these are the students talking again, we are trying to implement a cutting-edge e-learning environments based on SAGE. So we don't have time today to go into all the difficulties of collaborating over distance and using all kinds of teleconferencing tools, but it can be difficult. And so SAGE is one new thing to put in the toolbox. It's very high definition, and when you don't know people and you need to work together, it really helps to see the nuances. So they're working together. Now I'm coming to the acknowledgments, doing probably ahead of time, right? So GCB is NSF funded program. We thank Mayor Nostrom, Supercomputer Support. That collaboration is under another NSF program called Partnerships in International Research and Education. Our friends at SAGE and NSF Research Assistance Grants, which supplement the funding for global cyber bridges. So we had students be able to go to Brazil and to China and meet the people they've been working with. And I thank you very much.
Thank you, Heidi.
So,
Any questions?
okay.
Everybody's taking a siesta.
That's fine.
Thank you, Heidi.
My pleasure. I'm just going to shut this down and turn it over to Andrew.
The last speaker for this session is Andrew Howard. I'm mixing up my H's. He's the manager of Advanced Communications Research at the Australian National University, and he has been in advanced R&E computing and non-R&E computing and networking for a few years. Thank you, Andrew.
Thanks, Jacqueline. I'll be talking to you today about using human networks to respond to global pandemic disease events. Just before I do, I'd like to give you the standard plug for the Australian National University. The Networks and Communications Group is researching and delivering world-class network facilities and services for our researchers and students. I'd like to talk to you today briefly about pandemic disease history. We'll look at some of the rapid response successes that we've achieved in SARS and avian flu, and I'll finish off with a description of the emerging infectious disease network. Over the past couple of thousand years, humans have been exposed to a range of pandemic diseases. Cholera, bubonic plague, influenza, typhus, most recently HIV and AIDS, smallpox, tuberculosis, leprosy, malaria, yellow fever, SARS, and a whole range of new and emerging diseases which we're encountering based on global warming. There are a number of factors affecting disease spread. Most significantly are the rapid increase in global population, urban density and overcrowding, and the facilities of global transport which allow rapid movement of disease vectors around the world. Influenza was first described by Hippocrates in 412 BC, and the first influenza pandemic recorded in 1580. We've noticed that there is a 10 to 30 year reoccurrence cycle in influenza pandemics. And recent discoveries are that there are enormous pools of influenza virus continuously circulating in wild birds. Some of the more recent influenza pandemics over the last century were the 1889 to 1890 Asiatic flu, which was an H2N8 variant. It had a very rapid spread and a high attack and mortality rate, causing over 1 million deaths globally. One of the most significant disease outbreaks in the 20th century was the Spanish flu in 1918, which is the H1N1 variant of influenza. This was first detected in March 1918, and by October 1918 had spread globally. The significant thing with H1N1 is that there were massive death rates among young, healthy adults who are usually immune to dying from influenza. The 1918 Spanish flu killed between 20 and 100 million people globally. The significant thing about this virus is it's the current form that is called swine flu that's spreading the world. In 1957, H2N2, the Asian flu, was first identified in China and spread around the world within a 6-month period, causing 2 million deaths. One of the more recent influenza pandemics was in 1968, when the Hong Kong flu, an H3N2 variant, influenza A, still circulates and caused 1 million deaths. Most of us here would hold immunity to H3N2, but not to the previous variants of influenza. In particular, H1N1, the strain that we're currently facing, it is very rare that anybody in our generation will have immunity. So the World Health Organization has published some quite interesting data on pandemic flu. There are a number of phases ranging from predominantly animal infections with few human contamination to sustained human-to-human transmission, widespread human infection in phase 5 and 6, and then a decreasing number of infections in the post-peak and post-pandemic periods. With the current flu outbreak, we're in phase 5, which is widespread human infection occurring. So, with the current influenza A H1N1 event, there is limited mortality being experienced around the world. However, our health authorities are wise to respond in the way that they have been. In 2003, there was a disease called SARS, which was a coronavirus outbreak, which occurred in Taiwan. The Taiwanese hospitals reached the point where their medical staff were quarantined within the hospitals. Around 50% of the medical staff had been contaminated with the disease, and they were rapidly running out of specialists to be able to provide public health. Fortunately, the access grid construction was underway in a number of centres around the world, including the National Centre for High Performance Computing in Chicago, and a number of centres around Australia. The Taiwanese doctors sent out a call for assistance on the APAN, Asia Pacific Advanced Network, and access grid mailing lists when the infection rates became critical. The request for assistance included a system for remote diagnostics, which allowed sharing X-rays, numerical instrument readings, and a shared whiteboard for analysis. There was also a need for audio and video sharing between multiple sites, and teams with technical and medical expertise were required to implement this. The response globally was quite amazing. Within a 4-day period, there was a rapid mobilisation of local and global resources. The Australian and US access grid communities at that stage were well established, so engaged with our Taiwanese counterparts to assist with node design, construction and applications. The global collaboration was quickly built and an application to test X-ray sharing was put into place within a couple of days. So the first call for assistance occurred on May 15. and a collaborative definition of the SARS grid node and hardware requirements occurred on May 17. The hardware orders were placed in the afternoon of May 17, and the first prototype node assembled 2 days later on the 19th of May. It was decided to build three access grid nodes initially to be installed into the quarantined hospitals. The installation and the technical teams were sacrificed and stayed with the equipment in the quarantine areas. Sanchung and Changchun were online on May 21. The Gen-L and the Taiwan CDC came online 8 days later on May 29. The first two hospitals, it was decided to expedite the equipment and install them, and then hold out the second phase of installations for a couple of days while we tested the applications. So you can see here that this was the environment while we were building the access grid nodes, and you can see the hospitals on either side. The access grid provides a fairly high-level toolkit to build these sort of applications. So the outcome of this was that the system was used extensively to provide remote diagnostic assistance for X-ray analysis. Specialists around the world collaborated to diagnose cases. This allowed us to provide a Follow the Sun service with specialists from all non-affected countries participating to perform analysis. The X-ray images were between 1 and 20 megs and were exchanged using the Globus toolkit, which was the contemporary grid toolkit of the time. So global collaboration really solves problems. Rapid global response by highly skilled individuals changes people's lives. We co-opted others to provide a range of skills in multiple disciplines. And this was an informal and self-organising event. So, to ensure that we implemented some of these lessons, we demonstrated the facility to national departments of health and the World Health Organization, who were remarkably impressed that we could put this sort of effort together in such a short time. As an ongoing outcome of this, the Emerging Infectious Disease Network was formed. I'll talk about the Emerging Infectious Disease Network later in this presentation. The next disease outbreak which we were called to assist with was avian influenza, the H5N1 strain. There was an initial outbreak in Vietnam and Thailand in 2004, with further cases rapidly detected in Cambodia, Indonesia and China. The first human cases of mortality occurred in Turkey and Iraq within a 3-week period of the initial outbreak. So, to move on to the Emerging Infectious Network, it's coordinated by Dr. Anne-Marie Kimball at the University of Washington, one of Jacqueline's colleagues, and there are participants from all of the Asia-Pacific countries. The Emerging Infectious Disease Network holds a number of activities. We run biannual desktop exercises involving our government health agencies, which model typical pandemic responses in each of our nations. We hold an annual group meeting using video conferencing, and there's sporadic email on a list which typically increases rapidly during a disease outbreak event. One of the key things about EINet is that it typically just sits in the background as a quiescent resource that's available in case of a disease outbreak. To keep the organisation lightweight, we have a mailing list. We run regular video conferences, basically just to provide a testing facility. And one of the key aspects we've been able to provide is facilitating some of the less developed Asia-Pacific nations to participate by sponsoring representatives to attend the meetings. One of the most difficult issues we've faced in the Asia-Pacific region, particularly for the less developed countries, is that their telecom providers are typically monopolies. So it's remarkably expensive to provide a high bandwidth service capable of supporting the access grid. we found it cheaper to actually fly the Department of Health officials to Australia or Japan or to the US to participate in person. One of the most notable ones was Papua New Guinea, who participated in the last EINet event. Since 2004, there's been a rapid growth in network capability in the Asia-Pacific region, with the TN2 and TN3 networks linking most of the Asian nations together with high-speed network capability of 622 or 1 gig. This has allowed us to provide a number of extra facilities based on access grid, and also provides the capability for our European colleagues to participate in this initiative. There has been a significant growth in social network environments and also in use of the internet since 2004. MySpace, Facebook, LinkedIn and wikis. However, mailing lists are still essential for the old school users on the network. The social network sites focus more on the contemporary users, but the old internet users are still highly email dependent, so mailing lists are a key communications form. However, EINet is working across some of the newer social networking facilities and bringing in some of the more contemporary internet users. I'd like to talk about some of the grid environments that we're looking at implementing as part of EINet. The EU-Asia grid is a unique collaboration between the EU and many Asian nations to promote grid use in the Asian region. In that the access grid was an essential response for SARS in Taiwan, we have a pervasive grid infrastructure based on EGEE, which we can build on to implement the lessons learned during the SARS outbreak with the access grid. EU-Asia grid provides significant CPU and disk capability distributed over Asia and Europe with a single virtual organisation. However, we need the community to build the applications and engage their local communities and departments of health. I'd like to mention a critical component to all of these activities, and that is nodal individuals. That is people like those in the room who are well connected and can change the world. You know who you are. We need you to assist when a pandemic occurs. We need you to engage your networks of people, and you can make a difference. So the EU-Asia grid is a collaborative grid project combining Asian participants with programs covering high energy physics, health and storage. One of the significant parts is the health grid, which will be holding a meeting in Berlin between the 29th of June to the 1st of July. I'd like to invite any of you who are interested to participate in the health grid meeting. So, in conclusion, human networks are a way we can handle global problems. Well-connected individuals are the key. We can bypass bureaucracy. We can fast-track activities. A few well-meaning people can change the world. It's in your hands. You can make a difference. We need your help. Thank you.
Any questions? Come on, you're awake now. Time for coffee? Well, I've been beating those poor presenters into shortening their presentations. Now we have too much time. So please talk to them at the break. And thank you for coming.